Discuss the energy order of molecular orbitals in octahedral complexes. I am Dr. Devang Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Point to discuss. Today we are going to discuss the relative order of energy of different molecular orbitals, strong ligands, that is low spin complexes, weak ligands, that is high spin complexes, and filling of molecular orbitals with electrons. In addition to that, we're going to discuss today for one molecule, that is titanium hexaaqua plus 3 complex, and we're going to learn how to generate molecular orbital diagram for these say octahedral complexes, only sigma donation. A relative order of energy of different molecular orbitals, in which we have already stated that the 6 atomic orbitals of the metal ion overlap with the 6 ligand p sigma combinations, that is LGO ligand group orbitals, and generate 6 BMOs. 6 BMOs include A1G, that is 1, T1U3, EG2, and 6 ABMOs, which includes A1G star 1, T1U star 3, and EG star 2. So this 6 BMOs and 6 ABMOs is going to be generated by the overlapping of atomic orbital of metal transition series, the 3D metal ion, and LGO ligand group orbitals. BMO have lower energy than ABMO. Mind well, when you are drawing MOED, please keep this thing in mind that you need to show BMO having lower energy, even lower than that of LGOs. LGO has lower energy than AOs of metallic element, and that way we're going to study this energy ordering as well in this lecture. Now, overlapping orbitals of metal ion, non-overlapping orbitals of metal ion. For T2G orbitals, we have 3dxy, 3dyz, and 3dzx. These are non-overlapping orbitals. That means it won't participate into overlapping, and therefore they are remain non-bonding. Their energy remain unchanged. What it means? Their energy remain as equal as the energy of atomic orbital of 3D for the metal ion. For strong sigma bonding, BMOs such as A1G1, T1U3, and EG2 will be lowered in energy, and corresponding ABMOs such as A1G star, that is 1, T1U star 3, and EG star, that is 2, will be raised in energy compared to the energy of the 6 ligand orbital combinations, that is 6 LGO. Now, how strong ligand, or we can say how we can brand the ligand as a strong field ligand, or we can say how we can say that the formation of metal ligand combination in octahedral complex become low spin complex. So here we are going to discuss regarding strong ligands, strong field ligands. If the ligand present in a given octahedral complex are strong ligands, then it's going to form a low spin complex. It means that the energy gap, that is delta O, splitting energy between T2G and non-bonding orbital, T2G that is non-bonding orbital 3dxy, 3dyz, and 3dzx, and EG star, between these two, EG star that is ABMOs, is greater than the electron spin pairing energy. Electron spin pairing energy, that means when overlapping take place and two electron occupy in the same orbital, mutually their spin turns opposite direction, and at that time whatever energy generated, that is called spin pairing energy. And if this spin pairing energy is lower than that of the splitting energy, that is delta O, then we can say that the ligand is going to be more strong and it can split the orbital more effectively, and as a result of that, low spin complex is going to be formed. As a result, that the relative order of energy of different molecular orbital in low spin octahedral complexes we can see in this strong ligands and low spin complexes. The order of energy would be 6. This is the energy order of MO. Here there should be ligand group orbitals, and here that should be atomic orbital of metal. When you see in the previous lecture also, when we have shown you the MOED for octahedral complex, only sigma donation, this is the arrangement. Now this is only MO is shown over here. So in MO you can see the lowest energy is of A1G, that is sigma S BMO, bonding molecular orbital. Upper to that we have 3 sigma X, sigma Y and sigma Z, that is sigma P orbitals, and it is represented by Mulliken terms T1U. Above that we have energy, that is sigma dz square or sigma dx square minus y square. It is 2, that is Eg, that is sigma d orbital either you can say, or either you can give a Mulliken term as Eg. So this is the BMO, bonding molecular orbital, 1, 3 and 2, that is total 6 BMO would be there. And then after BMO, here we have 6 LGO, ligand group orbital. So ligand group orbital is little higher in energy compared to this BMO, which is lowest in energy. And in chemistry, lower the energy, more the stability. So the electron which is donated from LGO should be entered into this BMO. That we're going to discuss later on how to fill up electron in these orbitals. But about this, we have 3 non-bonding atomic orbitals, that is 3D XY, 3D YZ and 3D ZX, because they lie into the axis, between the axis, that means in a planar side, an approaching direction of the ligand would be on an axial side. They will not participate in overlapping, hence their energy remain as similar as the energy of 3D atomic orbital of transition metal ion. So here there should be a 3D transition metal ion, the energy level would be like this, and at the same level we have 3D XY, 3D YZ and 3D ZX. It means pi d orbitals, or we can say T2G as a Mulliken terms. Now above this we have Eg star, that is psi star d orbital, and that is psi dz square and psi dx square minus y square. And the difference in the energy between these 3 non-bonding atomic orbital and Eg star, that is called a splitting energy, delta O. And when the splitting energy if become greater than the pairing energy, because when electron enter into this BMO, mutually they will paired up anti-parallelly, and at that time whatever energy is going to be generated, if the that pairing energy is little bit lower compared to the splitting energy, then the complex is going to be formed is a low spin complex, and the ligand which approach to central metal ion is considered to be a strong field ligand. And therefore here we can see that there is only one electron as far as titanium hexaaqua complex is concerned would be there in this d orbital. Above this Eg star we have T1U star, that is sigma star p orbital, and above that we have sigma star A1G orbital. So these are 6 ABMO and these are 6 BMO. BMO is very closer to LGO, and therefore they will demonstrate the property of ligands, while this 3D which remain exactly equal energetic as metal atomic orbital, and therefore this will represent purely metallic characteristic, and this will represent metallic characteristic. It will remain closer to 4s and 4p. Therefore anti-bonding molecular orbital also demonstrate metallic characteristic, non-bonding T2G also demonstrate metallic characteristic, while this BMO which remain closer to LGO, they will going to represent ligand properties. Now weak ligands or weak field ligands or high spin complex. How weak ligand is going to form high spin complex, that we're going to discuss over here. If the ligands present in a given octahedral complex are weak ligands, that is high spin complex is going to be formed. Why? Because the energy gap, that is delta O, splitting energy between T2G non-bonding atomic orbital or molecular orbital, whatever you want to say you can, because it has the same energy as 3D. So between T2G and EG star orbital, that is ABMOs, between these two, if this splitting gap is smaller than the value of spin pairing energy, that is P is greater than that of delta O, will going to get high spin complex, and the ligand which approach to central metal ion cannot split the orbital more effectively, so the energy gap remain little lower compared to this spin pairing energy. As a result, the energy of T2G and EG star orbital become almost the same. It means there should be very minor energy gap between this T2G and EG star, and hence the electron can enter into higher energy level, and instead of being paired up, they will try to remain unpaired, and as a result we're going to get high spin complex. Hence the relative order of energy of different molecular orbital in high spin octahedral complex becomes, we can see slide. So this is the weak field ligand and high spin complex. Now here also you can see that sigma s, that is A1G, sigma x, sigma y, sigma z, that is sigma p orbital branded as T1U, and sigma z dz squared, sigma dx square minus y square, that is sigma d orbital, that is Eg, that is 6 BMO, remain lower in energy, above which we have LGO. Here we have 3 non-bonding orbital, that is T2G, D3DXY, YZ and ZX, and because the spin pairing energy is little less compared to splitting energy, the value of EG star is not that much high as we found in a strong field ligand or low spin complex. Here the value between these two T2G and EG star is such small that the electron from T2G should enter into EG star very easily, and as a result, instead of being paired up electron into T2G, electron try to enter and remain unpaired into EG star as well, and as a result we are going to get a high spin complex. Above this we have sigma star x, sigma star y, sigma star z, that is sigma star p orbital branded as T1U star, and above which we have highest energetic, that is sigma star s, A1G star orbital. This is for ABMOs. So and this is for ABMOs, and this is 2, 4 and 2, 6 ABMO would be there, but as the energy of this EG star is quite equal or little difference is there between these two, it is not considered as ABMO. It is having similar property as the T2G energy level should have, and hence we are going to get a high spin octahedral complex. Filling up for molecular orbital with electrons, MOED of octahedral complex, only sigma donation shows that we have 6 BMOs. Already we have discussed that A1G1, EG2 and T1U3, 6 ABMOs, A1G star 1, EG star 2 and T1U star 3, and 3 non-bonding d orbitals, that is 3dxy, 3dyz and 3dzx, which are available for filling the electrons. So these are the available molecular orbital between metal and ligand in which we need to refill the electron, we need to fill up the electron. Since 6 BMOs are nearer the energy level of the 6 LGOs, these BMOs are filled by 12 electrons donated by 6 ligands rather than the metal ion electrons, because it remains closer to LGO. Electrons of LGO which is donated to metal ion occupy in this 6 BMO. 6 BMO means 1 A1G, 2 EG and 3 T1U. This 6 will be filled by the donation of 6 ligands, and that is how this bond is going to be metal ligand bond, in which the required bonding electron for bonding is donated by ligand, and therefore it is known as coordinating covalent bond. Thus, the distribution of 10 electrons from 6 ligands in 6 BMOs can be shown as this. You can see A1G, उसमें 2 electron जाएंगे, lower in energy. Then T1U will going to have 6 electron, and then EG, here you need to correct itself, because instead of EG it is written as AG. Typological mistake, it is EG, and they will going to have 4 electrons. So 4 and 6, 10 and 2, 12 electrons would be there in BMO. Either you can say that sigma S will going to have 2 electrons, sigma P is going to have 6 electrons, and sigma D is going to have 4 electrons. This is EG that you need to keep in mind. So this is BMO, and 12 electron can be refilled from LGO into it. Since T2G non-bonding atomic orbitals are pure metal d orbitals, because its energy is quite similar with the atomic orbital of metal, whereas EG star ABMOs have a major contribution from EG orbitals of the metal, that is dz square and dx square minus y square orbital. The electrons previously present in d orbital of free metal ion are accommodated into only T2G non-bonding molecular orbital and EG star ABMO if required. I write EG star ABMO if required because if you have a low spin complex, electron do enter from T2G non-bonding to EG star, and if it is a high spin, then the electron do remain into T2G only. But if it is a low spin, instead of being paired up into T2G, electron do enter into EG star as well, and that is why I have written if required over here. Thus, if we have an octahedral complex of metal ion having DX configuration, then 12 electron present in 6 ligands will occupy the 6 BMOs. Already I have told you that. And X electron, X I have written because we do not know about what metal we are discussing over here. This is a common discussion. So X electron, that means electron in a d orbital. Say for example, D1, then 1 electron is there. D2 configuration, 2 electron is there. Similarly D10, 10 electrons would be there. So that is the electron present into d orbital of the free metal ion will occupy into T2G non-bonding atomic orbitals if it is only high spin complex. But if it is low spin, along with T2G, it may enter into EG star, that is ABMO, and that is why I have written over here if required. Here we shall discuss the distribution of 12 plus X electrons in the following two type of octahedral complexes. One that is strong fill ligands, which is going to form a low spin complex, and the other one is weak fill ligands that is going to form a high spin complex. This information we cannot have it from given in this LFT, or we can say MO diagram. Let us have the example for that. The octahedral complex, we have the example of hexa aqua titanium. Hexa aqua titanium plus 3 complex octahedral compound contain titanium plus 3, form a stable complex ion with 6 water molecules. So central metal ion is titanium plus 3, and 6 ligands would be 6 water molecules. The structure around the titanium plus 3 is an octahedral. As you know that 6 ligand approach to the central metal ion is result into octahedral geometry, either D2sp3 or sp3d2 hybridization would be there. So here you can see that 6 water molecule approach to titanium from axial side, and it's going to form D2sp invert hybridization. The titanium has 5d, 1 4s and 3p valence orbital. Already we have studied in our first lecture, probably second lecture, that we need to find out the valence orbital of central metal ion, and we need to assign a proper irreducible Mulliken terms to this valence orbital. So here we have to find out that titanium contains 5d, 1 4s and 3p valence orbital that can be used in constructing molecular orbitals. Each water molecule must furnish one sigma orbital, which is approximately an sp3 hybrid orbitals, because this is a water molecule and it has sp3 hybrid orbital. So each water molecule must furnish one sigma valence orbital, which is sp3 hybridized orbital. We shall not specify the exact s and p character of the water molecule because we don't know which kind of character it should be, and instead we're going to brand it as a sigma valence orbital or p sigma orbital of LGO. So that is how we refer it in that way. The metal orbitals can form sigma molecular orbitals, and they are 3d x square minus y square, 3d z square, 4s, 4px, 4py and 4pz. So these are the metal orbitals which is going to form sigma molecular orbitals. That means they will participate into overlapping with 6 LGO and going to form sigma molecular orbitals. Since the sign of the 4s orbital does not change over the boundary surface, as you know that it is spherical in shape, it's spread into x, y and z orbitals uniformly, symmetrically, and that is why the proper linear combination of ligand orbital of 4s would not is shown as sigma 1 plus sigma 2 plus sigma 3 plus sigma 4 plus sigma 5 plus sigma 6. Either you can brand it by number, or either you can write as sigma plus x plus sigma minus x plus sigma plus y plus sigma minus y plus sigma plus z plus sigma minus z. Whatever you want, you can represent in that. Overlap of the titanium 4s orbital with sigma orbital of the water molecules. Here we can see how the pictorial arrangement of 4s orbital. You can see that 4s is a spherical in shape and all the 6 ligands approach from 6 direction of the axial side and overlap with the 4s orbital of the central metal ion, and that overlapping result into 6 sigma bond, sigma 1 plus sigma 2 plus sigma 3 plus sigma 4 plus sigma 5 plus sigma 6. So here you can see that this is the metal ion and this 6 point charges approached from axial side to the center. Energy levels in titanium hexa aqua plus 3 lobes will with the ligand sigma orbitals that have the proper sign and magnitude. The wave functions would be represented as this one. The wave function associated with s orbital, that is 1 under root 6 plus x minus x plus y minus y plus z minus z, or instead you can represent in this way as well. For sigma x, this is sigma x because already s orbital is shown previously, so this will omit the sigma s, but sigma x can be represented 1 under root 2 sigma plus x minus sigma minus x. Instead that you can write as c4 that is under root 1 2, that is constant, and sigma 1 minus sigma 3. Sigma 1 is sigma plus x and minus sigma 3 would be sigma minus x. So that is how this, either you may present in this way, either you may present into this way. Whatever is feasible to you, you can use it in the exam as well. This is also the overlap of titanium 3d and 4p sigma orbitals with sigma orbitals of the water molecules, that is p sigma orbital of water molecules, and this interaction will result into this three different way, and that you can indicate into formation. This is for d orbital, this is overlapping of titanium 3d, and for p sigma orbital with sigma orbital of the water molecules, p sigma orbital of water molecules. Either you may denote it by number, or as already I've said, either you may denote it by plus or minus axial, that means Cartesian. 3d x square minus y square and 3d z square orbitals are also equivalent in octahedral complex, and sigma x square minus y square and sigma z square are degenerate in energy. We have used all the three of the metal valence orbital in sigma molecular orbitals. We are left with 3d xy, 3d yz and 3d zx. These orbitals are situated properly for pi bonding in octahedral complexes. Since they are not on the axial side, they are in between the axes, that means on a planar side, and the approaching direction of ligand in sigma donation only, that is axial side, so they should not have any kind of overlapping, hence they will remain unoverlapped as atomic orbitals only, and their energy level would be as similar as the atomic orbital of transition metal series. However, since water is not good pi bonding ligand, we shall consider that the 3dxy, 3dyz and 3dzx orbitals are essentially non-bonding in hexa-aqua titanium plus 3 complex. They are non-bonding molecular orbital. The 3d orbitals are clearly equivalent in octahedral complex, and we have degenerate set, that is pi xy, pi yz and pi zx. When we are going to discuss regarding sigma donation as well pi donation, then the role of these 3d xy, yz and zx would be more crucial in formation of MOED of those complexes. But here, since we are discussing only sigma donation, there is no role of this pi orbital, hence they act as non-bonding molecular orbital. In order to construct the energy level diagram for hexa aqua titanium plus 3, we must know something about the relative energies of starting orbitals, that is 3d, for s, for p, and p sigma water molecule orbital LGO. In this case, p sigma water molecule, that is LGO, is more stable than any of the metal valence orbital, and hence when you are going to draw the MOED, you need to keep the LGO little lower in energy comparing with the AOs of the free metal ion. Atomic orbital of free metal ion should have higher energy. That means in MOED, LGO should come into lower energy, and 3d or orbital of free central metal ion for s and for p is going to be higher energy, that you need to show into MOED diagram. This is fairly general in metal complex, and in energy level diagram the ligand sigma valence orbital are shown to be more stable than corresponding metal valence orbital, and that is how BMO is going to be even lower in energy compared to the atomic orbital of central metal ion. It is also generally true that the order of increasing energy for the metal valence orbital in transition metal complexes is in this order. 3d is lower in energy compared to 4s, and 4s is lower in energy compared to 4p. There are three set of bonding orbitals and three set of anti-bonding orbitals. The virtually non-bonding pi d orbital are less stable compared to the bonding sigma d set, but more stable than anti-bonding sigma d set. The relative energy of the three bonding sigma set are not known. The order given in this figure, when I'm going to show you next to this, was obtained from a calculation that is beyond the level of our discussion, so I haven't included this into this. We must count every electron in the valence orbital used to construct the diagram in the figure which I'm going to show you just now. The complex is considered to be composed of titanium plus 3 and 6 water molecules. and each of the six sigma valence orbital of the water molecule furnish 2 electrons for a total of 12. You can see in this MOED diagram only sigma donation. This is LGO. LGO have lower energy compared to the free metal ion valence orbital. This is the free metal ion valence orbital, and just below there we can show sigma p orbital of water molecule, and each water molecule is going to contribute 2 electrons. So we have 12 total electron with LGO. That 12 electron is donated to this 6 BMO. Among 6 BMO, lowest energy is sigma S bonding orbital, then sigma EG, that is sigma D orbital, and then sigma T1U, sigma X square, sigma Y square, sigma Z square. So these are the 12 electron and that can be donated from the LGO to this BMO, and BMO has lower energy compared to metal atomic orbital. Now this pi orbital has similar energy with metal, so whatever electron is there in metal orbital, valence orbital of central metal ion, that is 3D, enter into this one. So in titanium plus 3, only one electron is present into 3D, and that electron enter into either any of these three, right? And when this electron transits from this T2G2Eg star, then we are going to get the spectra. So spectral information can be obtained from this one as well. This will purely indicate the metallic characteristic. This will purely indicate the ligand characteristic. And that is how the MOED diagram can be formed for titanium hexaaqua plus 3. Since the electronic structure of titanium plus 3 is 3D1, we have a total of 13 electrons to place in the molecular orbital shown in the above figure. 12 that is from ligand side, and 1 that is from 3D1 titanium plus 3. The ground state of titanium hexaaqua plus 3 is therefore represented as sigma S orbital bonding contain 2 electrons, sigma XYZ bonding contains 6 electrons, sigma dx square minus y square and dz square contain 4 electrons, and pi non-bonding, that is 3D XY, YZ or ZX, any one of these three will contain 1 electron. So the spin remain unpaired, 1/2, and as a result there is one unpaired electron present into the pi d level in the molecular orbital energy diagram of hexaaqua titanium plus 3, and hence the consistent with this ground state, titanium hexaaqua plus 3 is a paramagnetic in nature as it contains one unpaired electron and spin is half. The electron in sigma bonding orbitals are mainly localized on the water molecules, since the sigma valence orbital of H2O is more stable than the metal orbitals. The non-bonding and anti-bonding orbitals, on the other hand, are mainly located on the metal ion, and we shall focus our attention in the section to follow on the molecular orbitals that are mainly based on the metal and derived from the 3D valence orbital. This is enough from my side. Thank you for listening me unwaringly. I would like to read this quote. जो पहले क्षमा मांगता है वह सबसे बहादुर है, जो सबसे पहले क्षमा करता है वो सबसे शक्तिशाली है, और जो सबसे पहले भूल जाता है वो सबसे सुखी इंसान है. Thank you very much for listening me patiently, and if you have any query, doubt, please post on chat box in our Moodle.